Let's now consider solving Laplace's equation using the argument function. So typically, we'll be able to do that with the argument function, which is the imaginary part of logarithm, without moving the branch cut. The branch cut for log z and for log z plus 2 pi I k, or arg z and arg z plus 2 pi k, so there's a new notation there. They all have the branch cut on the negative real axis. And as long as we want to solve the Laplace's equation in some wedge that doesn't contain that negative real axis, that works just fine. So we can just use the ordinary argument. But if we want to solve Laplace's equation in a region that contains the negative real axis, we have to move that branch cut somehow. So the book talks about doing that in a fairly cavalier way. You just simply take a different branch of the argument that has the range going from there all the way to there, and that's fine. And as for humans, that works perfectly. But if you want to code this, well, you've got argument built into MATLAB or Maple or R or Python or something, and you want to write down a solution of a problem using that thing. So how do you fix that? Turns out there's a really nice way to fix it by using the Heaviside unit step function. And this function is 0 if x is less than 0, and it's 1 if x is bigger than or equal to 0. Now, there's in fact some argument about whether it should be 1 for x bigger than 0 and then something else exactly at x equals 0. In fact, we don't need to have anything in particular happen at x equals 0, because what we're going to do is we're going to use this to move the branch cut somewhere outside of where we care, and then whatever happens exactly on the branch cut is not really very interesting for us. So if we think about it a little bit, we realize that this function, some constant times a Heaviside unit step function times some analytic function inside, as long as, some real valued function of z inside, is actually going to make perfect sense. Wherever this is positive, this thing is going to be 1, and this will be this constant a. And wherever this is negative, then this thing will be 0, and the whole thing will be 0. So this thing switches between 0 and whatever this constant a is, depending on what happens on the inside. So argument of z will go negative when z becomes in this half of the plane. And this thing might also switch sign as we cross this place. So we have to think about that a little bit. But away from the places where this thing changes sign, it's just a constant. And if it's a constant, then it's also harmonic, because the second derivatives with respect to x and y are both 0. So, for instance, let's take f of z to be arg z if 0 is less than arg z less than or equal to pi. So we want arg z all the way around with closure on the top, as arg z actually does. So arg z actually goes right up to pi on the top. And down here, we don't want arg z at all. We want arg z plus 2 pi. Why 2 pi? And that's because this thing is equal to pi here, and it's equal to minus pi on this side. So if I add 2 pi on this side, I will bring that slice up so that it matches, and we'll get exact matching on that part. So if we add 2 pi there on this part, from minus pi less than arg z less than 0, what we've done is we've exactly moved that branch cut all the way around to this side, because now the discontinuity will occur when argument of z is actually equal to 0, because on the bottom half we'll have 2 pi, and on the top half we'll have 0. So we'll still have a jump of 2 pi, but we've moved the jump over to this side. So this will allow us to solve this particular problem. Well, we can write that in terms of Heaviside unit step function with exactly this way. We'll choose a equal to 2 pi, and we'll choose the c equal to 0, and we'll choose the b equal to minus 1. And this thing cancels the discontinuity on the negative real axis because we have this jump of 2 pi, exactly canceling the jump down of 2 pi as we cross this way. And it moves the branch cut to arg z equals 0. So I'm really happy about that. Well, this is such a neat trick that in fact it works just fine if we move the angle to any angle theta. So arg z is always between minus pi and something. So if we suppose we want to cut it off at this angle theta here, which happens to be negative, then for minus pi less than arg z less than this angle here, we make that equal to arg z plus 2 pi. So that cancels the jump on this side. And then for this angle theta all the way up to less than or equal to pi, we make it arg z. And there's no discontinuity anymore because as we cross arg z equals pi, this arg z jumps down by minus 2 pi, and we've added 2 pi back in. So this thing has moved the branch cut not to 0, but just to some angle theta. And that's it. So this function, argument of z plus 2 pi times h of theta minus arg z, is what the book means by taking arg theta. So they choose an angle theta, and here's a concrete instantiation of the argument function with the branch cut moved to angle theta.